Okay, thanks for that. I'll make a start. So, okay, I've not got any more syntax to teach you. Well, maybe one or two tiny little bits and pieces. So first of all, this afternoon, I'm going to give a talk which is really just a collection of handy hints and tips, things to do, things not to do, practical advice for OpenMP programmers. So these are things that I've collected through over the years. So I see students making mistakes or things that trip up people who are new to OpenMP. And also from answering questions on the OpenMP website forums. So, these are some common questions or common things that crop up as issues for users. So something to watch out for is with your directive is that depending on the compiler, then mistyping the Sentinel. So if I leave out the $ in Fortran, or I mistype OMP in C++, that will often raise no error message. So the compiler will happily ignore anything like that. So be careful. It's a lot of the time, if it's parallel loops, parallel regions, what you'll find is that you just don't get any. You just end up with sequential code, which is annoying but harmless. But there can be examples. For example, if it's critical or atomic or something like that, then you end up with a race condition that you didn't want, and so on. So yeah. Be aware. One thing you could consider doing is, if you know that you're prone to certain typos, is just to write a little script to scrape your code every now and again for them. I mentioned near the beginning that the reason for the design of the Sentinels is that it helps you write code that works without OpenMP as well as with. So something else that helps is that there is a standard macro. So _OpenMP is defined if the code was compiled with the OpenMP switch turned on. So that's a standard way that you can use to conditionally compile code so that it works with and without OpenMP enabled. There is also a set of dummy OpenMP library routines in which you could link, but I think on the whole, if the preprocessor route is a better way to go if you want to have the source code work with and without OpenMP. This one's creeping a bit into performance issues, which I'll cover in much more detail in the second talk this afternoon. But it's good to be aware that have a rough idea in mind of how expensive is it to create threads and have parallel regions. On most systems, the overhead of executing a parallel region is around the kind of tens of microseconds range. So depends on the compiler, depends on the hardware, depends on the number of threads, but it's of that sort of order of magnitude. So that means that the sequential execution time of a section of code has to be bigger than that, several times bigger than typically, to make it really worthwhile parallelizing it. occasionally faced with the situation where the runtime of the code in a parallel region varies from one instance to another during the run of the code. So if that's the case, then you can use the if clause on the parallel region to decide at runtime whether to go parallel or not. Okay, so Jackamas, do I have a number of overhead in CPU cycles? Well, so most processors these days have a clock of around 2 gigahertz. So we're talking this sort of tens of thousands of clock cycles. Yeah. So it's quite small, but it's not nothing. Okay. So the overhead on so what the if clause does is that if the expression in the clause evaluates to true, then it goes ahead and executes in parallel. If it evaluates to false, then it will just execute on a single thread. The overhead on one thread is again, it's not 0. It's typically much smaller. It's a tenth of a microsecond. So it's a couple of the overhead on one thread is a couple of order of magnitude less than it is on more than one thread. Okay, so it's a reference there to a micro benchmark suite that I originally wrote a long time ago and is still evolving. But so if you want to measure do some detailed measurements of the overheads on a particular system, that's where to go for it. Okay, so question you often faced is, okay, I've got a loop, and is it parallelizable? So a really quick and dirty test is just to run it backwards. So this really, it's not infallible. Counterexamples are a bit hard to construct, provided that the loop iterator actually appears somewhere in the loop. Okay, so as long as the loop iterator is used, for example, to index into arrays or something like that, then it's quite hard to construct counterexamples where this doesn't work. The loop iterator never appears, so it's essentially just a like a time stepping loop. Then this doesn't work really. Next one is loops and the no wait clause. So if you remember what the no wait clause does is it gets rid of the implicit barrier at the end of the work sharing construct. And so if you have multiple loops, then you might ask yourself, when is that safe to do? So suppose I have a case here where I have a parallel region with 2 work sharing loops inside it. And the first one writes some values into AI, and the second one reads from AI. Okay, so the question is it safe to remove the barrier at the end of this loop? And that question really translates into, well, am I guaranteed to get the same mapping of I values to threads in both these loops? And the answer is yes, provided these conditions hold. So as long as the number of iterations in the loops is the same, and the schedules are the same, and they must be static, but you can specify a chunk size. So either static or static with a chunk size is okay. In that case, then you are guaranteed to get the same mapping of iterations to threads. And therefore, this case is safe to put the no wait on here. So as soon as a thread has finished its subset of iterations for this loop, it can go straight ahead and execute in this loop without waiting for the other threads. Strictly speaking, if you don't put a schedule clause on a loop, then what happens is actually implementation defined. So in principle, it doesn't have to be static. Though in practice, in all the implementations I know of, I've never seen an implementation that doesn't do that. But it's probably it's maybe not good to necessarily rely on that. So you should also note that static doesn't completely specify the distribution of the loop iterations. So really, the message here is basically don't write code that relies on a particular mapping of iterations to threads to work. Because you might get some nasty surprise at some point with it, for example, if you change compiler. Another thing about the schedule clause is to do with tuning the chunk size. So you're often faced, if you have a load imbalance situation, and you might either want static schedule with a chunk size or dynamic schedule with a chunk size. But doing the tuning can be quite tricky because the optimal chunk size can depend quite strongly on the number of threads, and you don't necessarily know how many threads are going to be used to execute the code. A better strategy is not to try and tune the chunk size directly, but to tune the number of chunks per thread, and then calculate the chunk size from that. So the chunk size expression in the schedule clause does not have to be a compile time constant. It can be a variable expression, which allows you to do this. It allows you to compute chunk size at runtime and use other things to tune. So number of chunks per thread is a more robust tuning parameter in general. In OpenMP, we have these two mechanisms for executing a block code on just one thread inside a parallel region. You can either use single or master. Which one should you use? Well, master has lower overhead because basically to implement it, there's just a test, whereas single requires some synchronization between the threads. Then if you do use master, you have to remember that it doesn't have an implied barrier. If you want the threads to wait at the end of the master, you have to put in an explicit barrier directive. On the other hand, okay, what do you mean by it's just a test? Okay, so master really is just if my thread ID equals 0, execute this block of code. That's all the implementation is underneath. Whereas for a single, there has to be some flag that indicates that some thread has already reached here. so that any later threads know to skip over the block. And in order to do that safely and correctly, it requires some synchronization between the threads. And there are other things about there's more bookkeeping that has to be done with single, because if you use single with no weight, there's the potential for multiple single regions to actually be executing at the same time. So there's more work for the runtime to do to keep track of stuff properly. But on the other hand, if you are in a situation where you do expect some threads to arrive before others, then it's good to use single. So if you're in a situation where you think where you have some reason to believe that some thread is going to arrive earlier than others, and that isn't necessarily thread 0, then it's good to try and overlap that computation with what the other threads are doing. So data sharing attributes, don't forget that private variables are uninitialized on entry to parallel regions. That's a very common source of a bug. So Tom asks, if multiple single regions can be active, can we use single to do things concurrently? The answer is yes, but it's usually not the best way. So I haven't talked about tasks in this course, but most of the possible use cases for concurrent single regions are much better solved by using tasks in OpenMP rather than trying to do it that way. Okay, Wouter asks, is there some kind of anti-single for maybe the rare case where you want all threads but one to execute a piece of code? So the answer is no. Okay, if you want other patterns, then you have to basically have to read the thread ID and do conditional execution based on the thread ID, which is less pretty, but yeah, that's the only way you can do that. Yeah, I guess I can't think of a case where you would want all threads but one to execute it, but you didn't care which one didn't. That would be a bit harder to code. You could do it, okay? Yeah, but it would be a bit messier. Yeah, you'd need a shared counter. You could do something like you have a shared counter that's initialized to one less than the number of threads. And then as threads went through that block of code, you test that counter and decrement it and take care to synchronize it correctly. Yeah, could be done. Okay, yeah, private variables are uninitialized. You can use first private to initialize them, but it's more likely to be an error because use cases for first private are surprisingly rare, actually. Okay, so it's more likely to be an error in the sense that you could probably get away with shared, or that you really did need to initialize it to something? So fixing it by using first private is possibly not the initialization that you really wanted. Okay. Okay, so I'm just going to have another rant about default none. So default behavior for parallel regions and work sharing constructs. Actually, well, okay, it is default shared. So you can't do anything about the work sharing constructs, but for parallel regions, then you can say default none. So it is probably the worst design decision ever. And really, trust me, just use it out of habit automatically, and just try and forget that the default behavior without a default clause actually exists at all. So I mean, the reason is quite weird actually. I've seen, I've observed lots of people writing, and people starting out with OpenMP and writing code. And it's quite amazing to watch people looking at a block of code and trying to list all the, trying to mentally list all the variables that are accessed and need to be thought about. And it's just amazing how people miss things. There are variables that you just tend to skim over and not notice. So it's just really, really easy, even if you think it's a fairly simple piece of code, it's very, very easy to miss stuff. So I just can't recommend this highly enough. Okay. So I say this is a bit of an artificial example here. Okay, but okay. Can anyone spot what the bug is in this example? Yeah, okay, so yeah, A is shared by default, but that's okay because different threads are going to write different parts of A. Okay, and Tom says I and J are shared. That's almost the right answer. I will be private by default because it's the parallel loop iterator, but J isn't. Yeah, so absolutely right. Yeah, J is shared by default here. Okay. So I know that this is a bit of an old-fashioned example. Most people don't write. Most people do the declaration inside here in modern C or C++. But it's people also tend to miss temporary variables and things like that as well. Okay. The nasty thing is that you may, if you compile this code with sufficient compiler optimization, you never see the race condition. Because in fact the value, if with things like this and also with temporary variables as well, if you have enough compiler optimization, then you may find that those values are never actually stored in memory, so that any amount of testing with those particular compiler options will never trigger the bug. But then you ship the code and somebody else compiles it without compiler optimization, or uses a compiler where the optimization behaves differently, and suddenly you have an exposed race condition. So it's really, really nasty. So you use default none and pick up these little horrors. So should you always test without optimization? Yeah, it helps. I guess it probably helps expose race conditions. Yeah, not a bad thing to do. I say, you know, your standard kind of testing is not guaranteed to pick up race conditions. You can test this till you're blue in the face, and the race condition never gets triggered under your particular conditions, and then you run it under, for example, you then run it on a loaded system, and the thread timing behavior changes radically, and suddenly you expose a race condition. So your standard ways of standard testing is for race conditions. It's never 100% reliable. Okay, this is probably a rare case, but it's nasty because you just can't. It's something you just can't do because you don't know. The compiler will do something, but you don't know what it's going to do. Okay, so the example here is, suppose I have a global variable foo, and then I have a parallel region, and I make foo a private. I make private copies of foo. This parallel region calls a function, and inside that function there are also accesses to foo. So the question is, what does that refer to? Okay. Does that refer to the original global copy via the extern statement, or does it in fact refer to the private copy in the enclosing parallel region? And the answer is you don't know. So it's basically it's pretty much an unusable pattern, because different compilers will can behave differently here. So if you really want to access the private copy, then you need to pass it through the argument list, or you can use thread private here to get private copies of the global variable. This particular pattern is not usable in any sort of portable way. So the problem is to do with optimization. It's that this function might get inlined into this code, and depending on whether you do that or not depends on what the behavior. Depending on whether the compiler does that or not depends on what behavior you're going to get. Okay, so I think this question might have come up earlier. So, what do you do in what do you do in this situation? So this is something that I hope that nobody would ever write code like this these days, but you may be dumped with somebody's old-fashioned, ancient piece of Fortran code, and then say, yeah, okay, what do I do here? Okay, yeah, default none will tell you what you need to do, but it's still horribly tedious. Okay, then default none will tell you what variables you need to think about, but if there's hundreds of them, then figuring out for every single one, should it be private or shared or reduction, and is tedious and error prone. And if you get it wrong, then you might just get a race condition. So it's nasty. So how do you handle this? Okay. Well, one way to do this is basically to refactor the code. Okay. So take that block of code that's inside the loop and make it into a subroutine. Okay. So then all your loop temporary variables can be declared local inside this function, inside this subroutine. And everything else gets passed through the argument list. So that's just a sequential change to your code, which is much easier to test for correctness. So once you come to parallelize that, and hopefully you've reduced the you've had to think about the variables as to whether you can declare them locally or not, and how they're used, but you've done it in a way which is easily testable as to whether you've got it right or not. Okay, and so this is largely a Fortran problem, because C++, you can make sure you declare temporaries inside the scope of the loop body. And again, if they're not, if that's not already the case, then again, that's a sequential refactoring change, which is amenable to conventional testing. Okay, this is a nasty one. Excuse me. So sometimes you have this pattern where you have a loop with a reduction variable in it, and you're inside a parallel region. So you actually want the result of the reduction later on in the parallel region. So that means that the reduction has to go on the work sharing directive here, so that the reduction computation happens at the barrier at the end of the loop, and not on the parallel region itself, because in which case the reduction doesn't happen until down here. But you have to be careful about the initialization of some here of the reduction variable. So remember that I'm inside a parallel region, and so what's going to happen is that every thread is going to do this assignment to 0. And worse than that is that there is no synchronization at the start of the loop. So what's possible that could happen is, well, there's actually a subtle race condition here. What can happen is that the assignment of the partial sum, the addition of the partial sum from one of the threads back into the original value here, might happen before another thread set the original value to 0. So it's possible to lose some of the partial values here. Nasty. So the solution is that, well, this is technically a race condition anyway, so you shouldn't, even though every thread is writing the same value, you shouldn't do that. But so what you need to do here, okay? So in order to make this correct, you should put this assignment here in a single or master plus a barrier. And you're guaranteed that only one thread is doing the initialization, and that it happens before any of the threads get into executing the parallel. So Milena asks, this example, could I do first private sum with sum equals 0 before the parallel? Unfortunately not. The reason is that if you do a reduction on a work sharing loop, then the variable has to be shared on the enclosing parallel region. And the rationale for that is that it's not clear which, if you made some private here, then which private copy are you using for the original value in the reduction? So unfortunately that doesn't work. And it gets even worse if this code here is actually in a separate function and sum is declared locally, because then sum is private by default and you can't do this. So yeah, you have to do weird things like make it static or artificially declare it outside and pass it through. So there are some annoyances with this pattern. This is a nasty one. Okay? So sometimes you see people say, okay, I've got a sequential code. First, I want to turn this into OpenMP. The first thing I'm going to do is, before I touch any of the code, I will turn the OpenMP flag on the compiler. And you find that just doing that causes your code. So how can that happen? Okay, there's a couple of reasons. Okay, you might have a bug because your code isn't using save or static properly. So if your code assumes that the contents of a local variable are preserved between function calls, for example, that might cause it to break. The reason for that is that compiling the OpenMP flag, even if there's no OpenMP in the code, it does subtly change the compilation process, because it forces all local variables to be stack allocated and not heap allocated. So for sequential code, the compiler has a choice. Okay, it can choose what to do with local variables. It can put them on the stack or on the heap. And typically if you have large arrays, then the compiler will often choose to heap allocate those rather than stack allocate them. So the other thing that can happen is that you just that you blow your stack by doing this. Okay? Just adding the OpenMP flag causes some large data structure to get stack allocated rather than heap allocated, and you get stack overflow. And the reason this is done is because that's the mechanism that enforces the rule that local variables are private. Okay, so that's the OpenMP implementation enforces that by making sure that those variables are allocated on every thread stack, and that's how they get the private copies. We need to make sure that we use those correctly. The problem is that those things are then shared by default, and so particularly if you use save or static to do first time through code, that can be really problematic if the first time through is actually inside a parallel region. Okay, if the first access first time that function is ever called, and you have some first time through code based on a save or static flag, then that can be bad. Okay? It's not going to work because you don't know. You're going to end up with race conditions, and you may get that first time through the code executing twice. So you might need to rethink how that's done. Tom asks, are static globals okay in C if we're using them to keep the variable in the file scope? Yeah, they're okay. Yeah, they have their uses. So those things will be shared by default. All globals would be shared by default. That's one reason why you might run out of stack size. So if you do have large private data structures, it's possible to quite easily run out of stack space. And so how do you increase your stack space? Well, in OpenMP, the size of the thread stacks apart from the master thread can be controlled with an environment variable, which is OMP stack size. However, that does not control the master thread stack. So you have to do that in the same way as you would for your plain old sequential program. So depending on your compiler and operating system, might be a compiler switch. So on Linux, you might be using ulimit. The reason why this is true is that OpenMP can't control that, because when a process starts executing, the stack size is determined before the OpenMP runtime can ever be called. So it's OpenMP gets active in a program, it's too late. The choice of stack size has already been made, and there's nothing OpenMP can do about it. Okay, so we'll skip over this one quite quickly because I already mentioned it. As critical and atomic cannot be used to protect the same memory location or protect the same variable from multiple accesses by different threads. You find you want to allocate some storage whose size is determined by the number of threads. But then how do you know how many threads the next parallel region will use and how big this storage? Well, what you can do here is, because if you call OMP Get Num Threads outside the parallel region, that returns to 1, so there's no help. However, which is OMP Get Max Threads. And what that does is actually returns the value of a particular internal variable. So OpenMP has these internal control variables, or ICVs, and this one is the nthreads var internal variable. And basically you are guaranteed that the number of threads used for the next parallel region will not exceed that value. The only exception to that is if there is a num-threads clause on the parallel region. Otherwise, you can use this to safely allocate enough storage ahead of the parallel region and be sure that you had enough elements for every thread, for example. It's always possible that implementations can deliver fewer than you ask for. Okay, there are you look at the OpenMP specification, there's quite a messy flowchart that determines, that tells you the number of threads actually calculated. But the runtime always has a get out. It can always decide to deliver you fewer threads than what you asked for, basically to protect the system against your ability. Okay. Yep, so OMP Get Max Threads may indeed yield different values at different points in the execution, okay? Because every thread has its own copy of this internal control variable, okay? So if you have nested parallelism, that means that different threads can create parallel regions with different numbers of threads in them. Okay, and so OMP set max threads changes the value of this thing on the calling thread. So every thread can can internally inside the program set this thing to a different value. You can do that as often as you like through the program. And effectively, what the environment variable OMP num threads does is to set the initial value of this thing in the master thread, and then it can be set to something else inside the program. So you actually have a lot of control potentially. Okay? So mostly you don't use it. Okay, almost all OpenMP programs don't use that. They just use the environment variable and never set in the number of threads internally. It's very bad practice to hard code the number of threads into your program. I've seen cases where that's caused significant problems, and where somebody has actually written OMP set num threads 16 inside their code, and that's awful because it can be quite difficult to track that down. It could be that statement might actually occur anywhere and affect all subsequent parallel regions. So it's a really very nasty thing to do. So you should use this thing carefully. So that what the impact was that no matter what you set in the environment variable, some parallel region code always executed with 16 threads, and the result was that on some, if you have on some system which didn't have 16 cores, then you get too many threads and you get terrible performance. So it's generally it's generally good to avoid writing code that depends on there actually being a certain number of threads. For some parallel patterns, it's difficult to avoid, but it's best to think, best to try not to do that. If you do, then you should always, when you're inside a parallel region, call OMP num threads to check whether you actually got the number that you expected or needed, and fail gracefully if you did. So there are some settings in the environment that you can make to try and maximize performance, and these are not necessarily set to the right thing by default. Depends on the implementation. So first, OMP Weight Policy. So this determines what threads do when they're idle. Well, it doesn't really determine it. It's really just a hint as to what you would like the runtime to do with threads that are idle. So this is when threads are not doing anything. So it could be between parallel regions. It could be waiting at a barrier. It could be waiting to acquire a lock or enter a critical section. So any point where threads are not active, what do? So setting this to active encourages those threads to spin and consume CPU cycles rather than go to sleep. So that means that it's you have dedicated hardware resources. That's fine, and it makes it faster to reactivate the threads. Set OMP dynamic equals false. So this says again, it's something of a hint, but it says, please don't deliver me through fewer threads than what I asked for, just because you think the system is overloaded. Just give me what I asked for. Runtime still has a get out, but at least it's a hint to say, I really, really don't want you to do that. And the third one is to bind your threads to cores. OMP proc bind equals true will prevent threads from migrating between cores. And just to finish up a little bit about tools. So in terms of debugging tools, and so traditional debuggers that you tend to find installed on some HPC systems like DDT or TotalView do have support for OpenMP. That's good, but that's conventional debuggers and is not much help for tracking down race conditions. What you'll find is that just running under the debugger changes the timing of events on different threads. So it's perfectly possible that you see a race condition giving you the wrong answers, and then as soon as you put it under the debugger, you magically get the right answers. There are these race detection tools that work in a different way. So what they do is they capture all the memory accesses that your program made during a run, and then analyze that data for races which might have occurred. So this is it's a trace and post-analyze approach to race detection. So in particular, Intel produce a tool which keeps changing its name. So I think it's currently called Intel Inspector XE. It's part of the Intel tool suite. So if you have access to that, that's quite a nice thing. It does a better job of race detection than any conventional debugging tool will ever do. We already talked about timers, so yeah. So make sure if you use timers in OpenMP code, then really make sure, and you're interested in performance, then make sure your timer actually does measure wall clock time. So yeah, so do use the OpenMP timer, and in particular, don't use clock. There's a Linux clock routine, for example. What clock does is actually measures CPU time accumulated across all the threads in the process. So if you use that, then no wonder you don't see any speed up. If you parallelize the code, then the thing that clock returns will at best stay constant or probably increase. Okay, any questions? Is there any stick code analyzer that can catch some of the things I've mentioned? The answer is essentially no. Okay, race condition detection statically is essentially impossible. It's doable in a very restricted set of cases. But as soon as you have real code where you have function calls inside parallel regions and pointer aliasing or anything like that, you simply can't do any static analysis on it. Oh, okay, great. So that gives ourselves a 10-minute break. I'll start again at 10 past with the last lecture. And if you think of any questions in the meantime, then please go ahead. I'll see if I can answer them for you. Okay, so just before I start the last lecture, just like to mention that there is now a link available from the course webpage for you to give us feedback on the course. So we'll be very grateful if you spend a few minutes at some point filling that in for us. It's really helpful. Helps us to improve these courses, you know, especially in these difficult circumstances. And I will also send a reminder email around about that tomorrow. Last lecture then is all about performance. So this might have happened to you, or it might be about to happen to you soon if you are new to OpenMP. Okay. So I wrote my OpenMP program, and I checked it gave the right answers. That was great. So I ran some timing tests, and the speed up was, well, a bit disappointing. Now what? Where do I go from here? Okay. So if you haven't already been here, then you will be. So the way I like to think about it is, you know, where did my performance go? Well, it disappeared into some sort of overhead. So your processors were doing something that they weren't doing in the sequential program, or they were doing something slower than they did in the sequential program. And I like to think about this in terms of breaking down the overheads into different types. Okay, so the way I'm going to present it is that there are these 6 main sources of overhead in OpenMP programs. So that's and so I'll talk through all these in turn and what we can do about them. So sequential code, idle threads, synchronization, scheduling, communication, and hardware resource contention. And then the 6.5 one is compiler non-optimization. I'll mention that very briefly at the end. So let's take a look at these and discuss ways of potentially avoiding them. Okay, so number 1, sequential code. So this is a fairly straightforward idea. So in OpenMP, all code that's outside the parallel regions or is inside master or single directives is essentially sequential code. Only one thread is executing. And the amount of time that you spend in sequential code will clearly limit performance. That's just a simple statement of Amdahl's law. So for example, if I have my original code and if 20% of the original execution time, if I haven't parallelized that, then I can never hope to get more than 5 times speed up. So the answer in that case is very simple. If you have too much time spent in sequential code, then you essentially haven't finished your parallelization job. You need to find ways of parallelizing more code. OpenMP is nice in the sense that it does allow for this incremental parallelization development. So you can, you can take it one bit at a time and work like that. But that clearly leaves you open to the possibility that you haven't parallelized enough code, and the amount of time that's in the sequential code may depend on your input, or on your data set, or on your configuration as well. So in that case, you just haven't finished the job. Second one is idle threads. So this is a situation where some threads finish some piece of computation before others and have to wait for others to catch up. So the usual case in OpenMP is, well, one of the usual cases is threads sitting idle in a barrier. So you've seen that, that OpenMP uses barrier synchronization pretty extensively. At the end of every parallel loop or end of every parallel region is a barrier. And so if I have this kind of activity diagram here, then so each of these bars is a thread, and time runs from left to right, and the blue bit is useful computation, and the red bit is idle time. And if the useful computation takes different amounts of time on each thread, then clearly if there's a barrier at the end, threads will be idle until the one with the longest computation catches up and reaches the barrier. So that's just a straightforward load imbalance situation. What can we do that? Okay, if it's a parallel loop, then clearly you have all the different schedule kinds and chunk sizes at your disposal, and you can use the schedule runtime option to avoid having to recompile while you're experimenting. For more irregular computations, then using tasks can be helpful. That's a topic for the advanced OpenMP course, which covers tasks. But in that case, then the runtime takes care of the load. It's supposed to try and take care of the load balancing for you. Okay. Just one thing to note is that it's not always safe to assume that two threads doing the same computation will always take the same time to do it, because that may depend. The time taken to load and store data may be different on different threads, depending on whether or if that data is being cached somewhere. So just because every thread is doing the same computation does not always necessarily mean that they're going to take the same amount of time to do it. Another place clearly where we can have idle threads is critical sections. So in OpenMP, critical regions, atomics, lock routines, and if threads that are trying to get access to the critical section. Okay, so in this case, I've shown the green stripy thing is a critical section that can be only executed by one thread at a time. So if all threads arrive at that point at the same time, then some of the threads will have to wait their turn to get in. Again, so the red stuff here is the wasted idle time that threads are spending waiting to get into the critical section. So what can you do about that? Well, you can try to minimize the time that's inside the critical section. That's possibly helpful. So we're trying to cut down the code that's inside the critical section to the absolutely minimum required. The OpenMP critical regions are a global lock, but it is possible to use critical directives with different names to protect different bits of code if you want to. Use atomics if possible, so that definitely allows more optimization. And so the example that we saw was the ability to do concurrent updates to different array elements, for example, or potentially multiple locks if atomics are not applicable. Any questions so far? Okay, so so far that's all fairly straightforward and obvious, I think. How do you name a critical section? Okay, so the name just goes in brackets after the critical directive. and it's a global namespace across the whole program, actually. So those names are effectively global names in the entire program. A little bit less obvious is synchronization costs. Okay? So every time you synchronize threads, there's some overhead. Okay, even if those threads are never idle, because in order to synchronize, the threads must communicate somehow. And in fact, what's happening at the hardware level is that different cores are communicating via the memory hierarchy somehow. Okay, via the cache hierarchy in the memory system. That's the only way that they have to communicate with each other. Again, so many OpenMP codes are full of these implicit barriers, and they can be quite expensive. And it depends on the number of threads and the runtime and the hardware and so on. But again, typically we're looking at thousands to tens of thousands of clock cycles to do a barrier synchronization. So that can all add up. And obviously other things like criticals, atomics, and locks are not free either. And again, so I haven't talked about tasks, but creating and executing tasks also comes with some cost. What do you do to minimize synchronization overheads? Well, essentially, you have to think about the granularity of your parallelism and try to parallelize at the outermost level possible and minimize the frequency of barriers. So that may require you to do some reordering of loops and therefore potentially also of array indices as well. So you may be in a situation where if your innermost loop is parallel, then that may be bad because you're going to execute an awful lot of parallel regions and therefore barriers. So trying to move that loop, that parallel loop, further out and reorganizing your code like that maybe what you need to do. There's cases where you can get rid of the barrier with no weight, but obviously be careful because sometimes that's completely necessary to avoid race conditions. And again, atomics probably do have significantly less overhead than critical locks in most implementations. Okay. Next one is scheduling. If we create computational tasks, rely on the runtime to assign those to threads in some way, then you're going to incur some overheads. Some of that will actually be internal synchronization inside the runtime. Okay, so threads have to agree. So Alessandro asked, do atomics use stood atomics under the hood? C++ question. The answer is probably not. Okay, so they're probably implemented at a lower level than that. Okay? They'll be implemented at the assembly code level. It's probably okay to mix stood atomics with OpenMP. You don't really have any guarantees from from either specification that's going to work, but in most cases it's probably going to be right. So yeah, you probably can get away with using C++ atomics in OpenMP, even though that's not a standardized feature. So when debugging, could it be a good idea to use schedule static 1 to try and expose race conditions? Yeah, maybe. always make them more likely, but yeah, using different schedules is worth a try. Again, it's just, you know, it's always better not to write them in the first place. But hey, right, we're not all perfect. Sandra, is it better not to use any the standard library things like locks to mix up with OpenMP? As I say, yeah, it's probably okay. Yeah. So the using these, if it's synchronization constructs like locks or atomics that don't depend on notions of numbers of threads or don't really require any much in the way of internal state and so on, that's probably going to be okay. Sort of fairly low level things like that. Yeah, probably going to work. And you just have to have some slight worries about how portable that might be across different compilers. In these cases, when it was necessary, necessary to use them or necessary to, not quite sure I understand your question here. Necessary to mix them. No, it's just convenient, I think. Yeah. So in some sense, it's you know, atomics are nice because you specify the behavior once and for all at the declaration. Whereas with OpenMP atomics, you have to specify the atomic on all the accesses that you're making. So in some sense, the C++ API is nicer because it's a property of the it's a property of the data object. It's a property of the object, basically, rather than the property of the data item, rather than the property of the statement of the code. Fernando asks, is it always a bad idea designed to mix OpenMP and manual threading? Yeah, probably. Okay. There's things are getting better in terms of OpenMP specifying how it interoperates with other threading things, but at the moment, it's probably a good idea to avoid it if you can. Again, you may find that what works with one compiler doesn't work with another one. But there are situations where it's somewhat unavoidable. You may want to write, for example, you may want to write OpenMP code, and you want to use a library that uses some other threading mechanism. And that's okay, but you can get some nasty surprises. Usually what happens is usually just a performance problem. In fact, what tends to happen is that you can very easily end up with more threads than you have hardware resources, and threads not idling nicely because they don't know about the existence of each other. So you can end up with bad performance from that kind of thing. So yeah, it's not a it's okay, but It may work, but you run some risk of bad things happening sometimes. Okay, yeah, so schedule overheads. So, the examples of this would be, again, tasks, but also things like the non-static loop schedules. So, if I do something like this, if I have a loop with a very large number of iterations that doesn't do very much inside, then doing something like schedule dynamic 1 is likely not to perform very well, because the threads have to synchronize at every single iteration to decide which thread's going to get the next one. So this is often a case of getting the granularity of our computational tasks right. Okay, if you're, whenever we're splitting up our computation into different pieces for parallelism, if the pieces are too big, then you might result in having idle threads because you don't have enough parallelism, or it doesn't load balance nicely. But then if you make your tasks or pieces of computation too small, then that tends to result in too many scheduling overheads. So there'll normally be some sweet spot in the middle, or some optimum granularity that gives you the best performance. Okay, so on to some of the nastier and more difficult stuff, and this is all to do with communication. This is because on shared memory systems, communication is effectively disguised as increased memory access costs. So what's going on here is it takes longer to access data that's in main memory or that's in another processor's cache than it does to get it from the local cache. And you have to remember that memory accesses are relatively expensive things. It's order of 100 clock cycles for a main memory access, compared with a handful of cycles for a floating point operation. And the communication between processors takes place via the cache coherency mechanism, which I'll say a little bit more about in a minute. So unlike in message passing codes, the communication is very fine-grained and it's spread throughout the program in a way that's not obvious. So it's much harder to analyze or monitor. It's if you have those of you who've done MPI programming, it's very obvious where the communication's happening. It's inside the MPI library calls. In a shared memory program, potentially any memory access could be causing some communication to happen. So, or at least any access to a shared variable could be causing communication to happen. And it's very difficult just to look at a piece of code and decide when that may or may not be happening. And it's also hard to monitor as well, because it's on an individual memory access basis. Those are things that are very fine-grained. So getting tools that will give you sensible statistics or analysis on that is really difficult. Very briefly, okay, cache coherency is quite a complicated topic, but on one slide, okay, I can at least give you the basic idea and the basic model that you need to have in your mind programming. Okay. What happens is whenever a thread running on a particular core writes a data item, it will get an exclusive copy of that data item in its local cache. And any copies of the data item in other caches will get invalidated to avoid reading any out-of-date values. Once a write has happened, then any subsequent access to that data item by other threads has to get the data from where the exclusive copy is. And that takes time because it means actually moving data from one cache to another. So that might be, could be between caches on the same chip, or in a multi-socket system, it could be between sockets. Okay, so that's really a hugely simplified description of what's going on. So the reality is a whole bunch more complicated than that. But that's the basic idea. Okay, so whenever something's written, you get a copy in the local cache, and then other subsequent accesses will have to retrieve it from the place. What does that mean for writing programs? Well, data is going to get cached on the processes which are accessing it. And so you have to reuse cached data as much as possible. So this is really just an extension of what you need to do for sequential programming anyway. Okay? So for optimizing sequential code, you need to make sure that you use cached data as much as possible. But then this is with multi-threaded programming, you have this extra dimension in the sense that you want to write code with good data affinity. That means that in trying to ensure that the same thread accesses the same subset of program data as much as possible. And try to make those subsets at least reasonably large contiguous chunks of data. Okay, so see why having very fine-grained interleaving of accesses is bad in a minute. And also for this reason, this is another reason why it's important to prevent threads migrating between cores while the code is running. Because if a thread is accessing some data, it'll be cached in that local cache. If the thread moves to another core, then there's a cost of moving all that data with it. So here's an example. Okay. So we've got two loops here. And so let's look at the second loop first. Okay, this loop nest here. So I have the parallel for directive, which distributes the iterations of the I loop between threads. But the J loop runs from 0 up to I minus 1. So this is a badly balanced loop, and therefore you probably want to do, to choose some suitable schedule for it. Then if we look back at the first loop, okay, and so this loop is writing values into this two-dimensional array A, and the second loop is reading them. But this loop is not badly balanced, because in this case, J runs from 0 up to n minus 1. So you might look at this loop in isolation and, okay, I don't need to do anything special with the scheduling. So a plain old static schedule should be fine here. But then what we've got in this case is that the access patterns, so which thread is accessing which part of this array, is different in this loop from this loop. So for most of this array, these reads here will be to elements of the array that were previously written by some other thread. And if they were written by another thread, then the chances are they're going to be currently stored. The up-to-date values will be stored in some other cache. So these reads here are expensive. So this one is quite easy to fix. So what we could do is if we apply the same schedule to this loop as this loop, then we can ensure that the access patterns to this array match, and that anything that's read here will have been written by the same thread, and therefore hopefully will cache locally. Okay. There's another example here. So suppose I have a parallel loop that reads some elements of an array. And then I have a sequential loop that reassigns some values to it. And then another parallel loop that reads it again. So again, so what you will get here is that this means that you will have these parallel accesses, means that the elements of A will be stored across multiple different caches. These sequential writes will produce an exclusive copy all in one cache and invalidate all the other copies. And then these reads here will have to go to this cache that was written here to get the new values again. So you might look at your code and you might imagine that these two loops have a lot of computation in them and are reasonably expensive, but this one doesn't, and so you might think it's not worth parallelizing. But the act of not parallelizing this code implies a lot of communication of data between the different caches. Okay. Have we chosen to set it to be 16? Yeah, by experiment. Okay. Maybe it just turned. I just picked a number. Maybe it turns out to be the right one. Really, just to illustrate that 1 is not always the best choice here. So what you would see in this case, if you did some timing here, you would see that you see quite an odd effect. What you will see is that because of the invalidations that have to happen here, then this loop, which is a sequential loop executed on the master thread, will take longer if you have multiple threads executing these loops. It's quite weird, but it's quite a distinctive signature. So if you measure your sequential code and you see it taking longer as the number of threads, as you increase the number of threads in the parallel bits, then that's a good indication that this sort of thing is going on. The result of that is that you may end up needing to parallelize code, which does not appear to take much time in the sequential program. So in this case, it might, for example, be a good idea to merge these two loops together, if possible. So to merge this assignment into this loop. Okay, really nasty stuff, numer effects. So on multi-socket systems, the location of data in main memory is actually of some importance. So if you remember back to the original diagrams I had at the very first lecture, we have multiple sockets, then every socket has its own piece of main memory associated with it physically, even though we have support for the global space across the whole memory. So almost, this is true of pretty much any current x86 type system that has multiple sockets in it, and most current HPC systems have 2 sockets. And newer chips are even worse. So the new chips that are coming in ARCHER2 are the AMD EPYC ROMs. And they actually have 4 numer regions per chip. So they have 64 cores on a chip, and each set of 16 cores has its own piece of memory attached to it. But OpenMP doesn't have any mechanism for you controlling where your data is allocated in main memory. Basically, this is down to what the operating system does. And the common default policy, so certainly on Linux, is for the operating system to place data, okay, in the memory that's attached to the processor which first accesses it in the program. This is so-called first touch policy. And for a lot of applications, that makes a lot of sense. Okay? So if you're just running a single process, then wherever that process is running, it will get its data allocated on the same socket where it's running. Great. Unfortunately for OpenMP programs, this can be the worst possible thing, because if your data is initialized in the master thread, it will all get allocated on one socket. And then having all the threads or all the cores in the system accessing data on the socket can become a bottleneck. It basically restricts the amount of memory bandwidth you have available. What can you do? Okay, sometimes you have some operating system options to control the data placement. So for example, in Linux, you can use the numactl command to change the policy from first touch to round robin. So it will so memory allocation is done in pages. So this will cause the allocation to be cycled around the socket rather than done on a first touch basis. Or we can use the first touch policy to control the data placement indirectly by parallelizing your data initialization. Okay? So even though that may not seem worthwhile at all in view of the insignificant time that might take in the sequential code. And so you may have a long-running program, runs for hours, the data initialization is done once at the beginning, and it takes some fraction of a second. Why should I bother parallelizing it? Well, it has this long-term persistent effect on the performance of the rest of the program, because that's what controls where the data is placed in main memory. You don't have to get the data distribution exactly right, and having some distribution is usually much better than none at all. If your data structures are big arrays, big rectangular arrays, then this is relatively easy. If your programmer has much more complicated data structures like trees or graphs, which are built organically in some way, then it can be a whole bunch harder. And you just have to remember this allocation is being done on an operating system page basis. So the size of these allocations are several kilobytes. And it's an argument for not using large pages actually. And then the last nasty thing is false sharing, though to be fair, this is getting better in recent hardware. So this is not, it still exists, but it's not as bad as it used to be. And this nasty effect is caused by the fact that when we talk about these cache coherency operations, acquiring exclusive access on data items and doing invalidations and so on. These are done on cache lines. So the these units of data are typically sort of 32, 64, 128 bytes long. And so in other words, always bigger than a single word. So what that means is that if you have a situation where different threads are writing to neighboring words in memory, that can cause this communication. So even though the threads are not accessing the same words, they're not accessing the same data, there's no actual communication implied by the program, but nevertheless, communication can still be happening underneath in the hardware. And it's still a problem if one thread is writing and others are reading. So the worst cases happen, so you have to just be aware of patterns like this. The worst cases happen where you have threads repeatedly writing neighboring array elements. So for example, if you declare an array and index it by your thread number, that would be an example. Okay, so if you wanted to count something that's happening on every thread in a shared array, then if these updates are sufficiently frequent, then this will cause a load of intercache communication traffic. Another one is one of the reasons why chunk size of 1 is not necessarily optimal. Okay, so if my parallel loop indexes a one-dimensional array with frequent writes like this, and again I have and I use a static 1 schedule here, then I end up with neighboring threads writing neighboring words in memory, and again triggering this kind of problem. Okay, so last main topic is hardware resource contention. So because of economics and because we use commodity processors pretty much everywhere these days, the design of the hardware is a cost performance trade-off. And there are shared resources which, if all the cores try to access them at the same time, are not going to scale. Or if put it another way, it's a glass half empty, glass half full dilemma. An application running on a single core is able to access more than its fair share of the resources. So when you when you increase the number of threads, increase the number of cores that are being used, then access to those resources has to be shared out in some way. And the main ones you have to think about are cores, and therefore the threads that are running on them will contend for memory bandwidth. They will contend for capacity and potentially also for the functional units, for the arithmetic units, for floating point units, if using simultaneous multi-threading. So if we're using hardware threads, multiple hardware threads active, then they are sharing the functional units on the core. The main message from this is really to do with memory bandwidth. So codes which are very memory bandwidth hungry will not scale linearly on most shared memory hardware. So what can you do about this? Well, it's really just a question of trying to reduce the bandwidth demands by improving locality, improving the reuse of data in caches. And that should benefit your sequential performance as well, but it's particularly important for multi-threaded code. Okay, so I'll just very quickly run through an example of this with some real data. Okay, so this is a little experiment I did on the old. This is the old ARCHER system. Okay, so it's looking a bit dated now, but nevertheless, it's still entirely valid because a lot of the basic processor design hasn't really changed very much. Things have got faster. We've got more cores, but the same kind of issues are still there. This is an Ivy Ridge processor with 12 cores. Every core has its own level 1 and level 2 caches. And then there's a 30 megabyte shared level 3 cache for all 12 cores. So this is just one of the 2 chips in the socket. So I'm not considering any sort of NUMA effects here or anything like that. This is all running on one socket. So what I did was just do repeated executions of this piece of code. Okay. So all it does is it uses OpenMP to form the sum of an array. The question you can ask then is, what speed up can I get on different numbers of threads depending on the value of n here? So if I vary n from very small up to very large, how does the speed up change? And so that's what I've got on this next slide here. So apologies if it's looking a little bit small, but so what I'm plotting here is the speed up that I get against the number of iterations in the loop. And then do that, and then every line represents a different number of threads. So this is 2 threads, 3 threads, 6 threads, and then 12 threads on the 12 cores. You can see some interesting things here. So for small values of n, the speed up is awful. It's much, much less than 1. What that means is the parallel code is running much slower than the sequential code. And this is death by synchronization. Okay? This means that for small values of n, I don't have enough work in the loop to offset the overheads of the parallel region. But it actually takes, depending on the number of threads, it takes somewhere in the tens of thousands of iterations to even break even, to get a speed up of 1 and have the parallel code run faster than the sequential code. Okay. So that's just a sort of useful reminder of that you do really need enough work inside your parallel loop to make it worthwhile. Okay. Then once I've overcome that, on 2 threads, everything's pretty nice. I reach a speed up about 2, and it stays there. However, once I go to 3 threads, so that's the red points here, then I actually get this slightly weird effect where for a small number of n values, I get more than 3 times speed up. And that's because I've got more cache memory available on 3 cores than I have on 1. So that's a level 2 cache effect that's going on there. Okay. And then it settles down to something a bit less than 3 times speed up for large loops. And as you go bigger, for 6 threads, now I just about touch 6 times speed up. And then it settles down to something about 4.5 and then drops off again. And if I have all 12 threads running, then it maxes out about 8.5 for a bit, and then drops down to something less than 4. So in this regime here, the data fits in the level 3 cache. So by the time I get to 6 or 12 threads, there is some contention for the level 3 cache bandwidth, which means that this value is not 12 here. Then once the data is too big to fit in the level 3 cache, once I'm out here, then all the accesses are coming from main memory, and then the scalability is much worse. So by the time I get to about, there's actually less than 6 threads. By the time I get to about 4 or 5 threads here, I'm completely saturating the available memory bandwidth, and essentially nothing I do to my this is not OpenMP's fault. This is entirely a function of the hardware that's causing this lack of speed up here. Okay, so there's other things as well. So we also can be contending for cache space. So again, because of shared caches, if you run a single thread, then that probably has access to the entire cache. Once you start to run multiple threads, then that cache space has to be shared out between them. Hardware threads, yeah, Okay, so this is simultaneous multi-threading, or what Intel calls hyper-threading. And if we have threads, OpenMP threads running on the same core, they will contend for the functional units, so particular floating point units, as well as cache space and memory bandwidth. Using hardware threads can help performance. It tends to benefit codes where threads are idle because they're waiting on memory references. So codes with non-contiguous or pseudo-random scattered memory access patterns may benefit. But codes which are bandwidth hungry or which saturate floating point units like dense linear algebra might not benefit from this and may actually run slower. And then finally, we've also got oversubscription as well. So this is just basically the idea that running more threads than you have hardware execution units, whether that's cores or hardware threads, is generally a bad idea. What happens then is the operating system tries to give each thread a fair share of access to the execution units. But the cost of stopping one thread and starting another is high. Okay, it's more than thousands of clock cycles every time that happens. And it also ruins your data locality as well, because you get threads will often restart on a different core from where they were previously executing. Okay, so that's my 6. The 6.5 is this compiler non-optimization thing. So it happens very rarely, but it just might happen to you, and you wonder what on earth's going on. Sometimes adding OpenMP directives can inhibit the compiler from performing some of its sequential optimizations. So what you see here is that if you execute the parallel code on one thread, it may have a longer execution time than the sequential code without OpenMP. Can be a very tricky problem. So thankfully it's very rare. It does happen. It can be tricky to find a workaround because it's hard to figure out what it is that's what optimization is failing and why. Sometimes you can fix this by making this may be a reason for making private copies of some shared read-only data, or making local copies of variables inside functions can help sometimes. But say the causes are often difficult to determine, but thankfully it's a rare occurrence. Good. So can we have some overall strategy here? Well, yes. Okay. So, and this is not really very different from what you would do for optimizing sequential code. Okay. So in this situation where your code is giving poor speed up, I don't know why. Well, what do you do now? So I've convinced you and given you enough information that you don't take option 1 here. Okay. So the approach that I would advocate here is to try to classify and localize the sources of overhead. Okay? In other words, what type of problem is it? Which one of those 6 things is causing the problem, and whereabouts in the code is it happening? And use available tools to help you. So timers, hardware counter data for cache behavior, that kind of thing, profiling tools, all potentially used to try and help narrow this down. And then obviously, same as with sequential coding, you fix the problems which are responsible for the largest overheads first. No point fixing the small overheads while there's still some big ones around. And then once you fix one problem, go back and measure again and see where you are. Okay, so a little bit about tools for performance. So standard profilers, so things like gprof or the profilers that come with IDEs, tend to be very confusing in multi-threaded environments, because typically what they do is they don't distinguish between different threads. They typically accumulate the time spent in functions across all threads, which is A, but it can be just very confusing and not helpful. And sometimes you will see some of the runtime library functions coming up in your profile, and that can be helpful as long as you know, as long as you can decode the names, because that's, you know, those are compiler internal functions. But you can see, you can sometimes see barriers or critical sections turning up in your profile, which is a clue. You can get a lot out of using timers. So, you know, the one strategy that I tend to advocate is to add timers around every parallel region, as well as around the whole code, or at least the whole piece of code that you're interested in speeding up. And then at least you can, you know, work out which parallel region has got the bad speed up. So that gives you a long way towards localizing your problem. And again, remember that don't assume that the time spent outside parallel regions is necessarily independent of the number of threads. So if you have timers around every parallel region, timers around the whole code, then you can subtract and recover the time for the sequential code, which also tells you something useful. There are various performance tools around out there, so things like Vampire, Detune, Tau, Map, CrayPat on Crays, and all have various different capabilities. Most of these have some sort of multi-threaded capability, and will try to tell you something about performance. And most of these are commercial, so they depend. You know, it just depends on the system you're working on, whether somebody's forked out the money for a license or not. Alaska is quite an interesting one. It is free, and it does try to do this idea of that I've kind of gone through, breaking down the overheads into different categories. But essentially, none of these tools really deal very well at all with the kind of communication, number effect, or false sharing type problems. And one tool that I do know of that does do this kind of thing is called Thread Spotter, because again, this is working in a different way. It's basically taking a statistical trace of memory accesses. So it's a bit like the race detection tool, except it doesn't need to do. It's a bit more lighter weight because it doesn't need to record every memory access. It just takes a statistical sample of. But it can do. You know, by doing that, it's able to give you some statistics about the cache and memory behavior and pick up false sharing and things like that. Okay, my apologies for overrunning slightly. So, okay, does anybody have any more questions? Okay, so okay, OpenMP and BLAS and LAPACK. Okay, so you call BLAS routines from outside a parallel region, and these are shared memory parallel, or can you call those from inside parallel threads? The answer is you can. The answer is you can do both. Okay, but mixing them in the same program might be problematic. Because it may depend on. It really depends on how the multi-threading in your BLAS library implementation is controlled. So this is potentially one situation where you can end up with more threads than you wanted. It is a little bit library dependent. But generally speaking, it works. You can take either approach here. yeah, so you can try both. Yeah. So having OpenMP and sequential blars gives you a bit more control. But yeah, that may just be it's additional work to recode, to have to put some explicit parallelism into your matrix operations. Oh, good question. So why no default private in C++? I've spoken to compiler implementers about this, and I believe the reason is to do with the way that C and C++ compilers handle internal variables like erno, and that it's not clear exactly what default private would mean in those circumstances. I've never been convinced that's a really good excuse for not allowing it, but I defer to people who work on the compiler implementations on that one. You'd say that it's probably not that useful in C++. If you want, you can avoid most of the private declarations anyway by declaring variables inside the scope of the parallel region or the parallel, or whatever construct it is. Yeah, so parallel regions or also applies to tasks as well, which I haven't covered in this course. So, and I recommend that you strongly recommend, and I'm going to do that again, that you use default none anyway. So I'm not sure it's a big deal, as it's in practice that you can't use default private in C++. Great. So please do the practical exercises if that would be helpful for you. Very happy to answer questions on those, either on the chat board or if you want to send me code, then it's maybe more convenient by email. Either of those is absolutely fine by me. And so in 2 weeks' time, I'll have an open session to look at those and go through. So I'll answer questions and I'll maybe do some maybe just work through some of the examples live as well. So that's 2 weeks today. So in that case, thank you very much, everybody. Thank you very much for your attention and for all the excellent questions and discussion.